Welcome back to ECE 501B. If you look at the last announcement, you'll see that I'm already preparing for the end of the semester. Our final exam is on a Tuesday. So if you have a Monday, Wednesday schedule, since that's when we meet, I want you to be aware that our final exam is not on a Monday or a Wednesday. It's on a Tuesday. And it's a little later. It starts 2 hours later than what your normal class time is. It's Tuesday at 6 on the 13th of December. Between now and then, you'll have 2 homework assignments. I still owe you homework assignment number 7, but we only have 8 assignments in total, not 8 more. 2 more between now and the final. And the 8th one is due on the 7th, which is the last time that we will meet. And maybe you wondered what PROECT was, but it's project. My J somehow disappeared. So we have our project deliverables. The first one is due, project deliverable number 1 is due on the 17th, and the last 2, the project itself, is due also on the last day of class. Today what I want to do is finish up our discussion on what kind of operator does it take for that operator to be diagonalizable, to give us a nice structure if we're thinking about its matrix representation. We've already looked at what that requires in the complex spectral theorem. Our operator needs to be normal. We will talk about the real spectral theorem, but before we do that, we want to go back to earlier algebra classes and talk about completing the square and reviewing or reminding ourselves about the Cauchy-Schwarz, or the lower limit on the Cauchy-Schwarz, or the lower bound. And then we will introduce a couple of lemmas, 26 and 27, before we get into the real spectral theorem, which is what structure do we need on our operator in order for it to be diagonalizable when we're talking or when we're working with a real field of numbers. We'll then summarize what we've learned, how they compare or how they differ when we're dealing with a complex inner product space versus a real inner product space. When can we diagonalize an operator? Then we will start talking about more general ways of sort of decomposing a linear operator or a map. And that's going to require that we start talking about positive operators, which means how do they scale, contracting or expanding. That's what I'm meaning by scaling. How do you adjust sort of the length or the magnitude? That's the positive operators. We'll talk about definitions, theorems, proofs, examples. We'll talk about square roots of operators, and then we will talk about isometries, which are now rotations or directions. And that means then that if we can take a linear map and show how it expands or contracts and rotates in all the different directions, that's how we want to be thinking about decomposing a generic operator or map. And that will lead us into other representations beyond just diagonalizing a operator, because we can see after today that we can't diagonalize every operator because they aren't necessarily normal or self-adjoint, which are the 2 requirements to be diagonalizable when we're talking in or dealing with complex inner product spaces or real inner product spaces. Let's then recap where we've been briefly. The definition of an adjoint. That's now looking at the equality of 2 inner products, and in the idea or the concept again behind the adjoint is how do we move that linear operation between slots. If that linear map is in the first slot, how do we get it out of the first slot into the second slot? Well, we look at its adjoint, and the adjoint then allows those 2 inner products to be equal. And that's the definition of the adjoint, is how do we move that operation into the second slot. A linear operator T is normal if the operator and its adjoint commute. And there's two ways of thinking about that. You can just look at it in the obvious way, where t dagger, t times its adjoint is equal to its adjoint times t, or in terms of how you operate on those. Or you can think about preserving norms, where now for the same vector v, if you take the norm of tv and compare that to the norm of the adjoint of t with v, they're equal if that operator t is normal. So you sort of keep the norm normal, a way to maybe think about it or remember it. And then self-adjoint means that it's more than just normal. It's now t is equal to its adjoint, which in the above definition of the adjoint, if you had a self-adjoint operator, you could erase that dagger symbol, and that's what you mean by an operator being self-adjoint. TV, comma, W in an inner product would equal V, comma, T, W inner product if your operator is self-adjoint. Reviewing the complex spectral theorem that we talked about last time, it had these three statements that were equivalent. And we're separating when we talk about how can we diagonalize maps or operators. It should be an operator, since if it's now diagonalized, we're dealing with something that's square. We separated that into two different inner product spaces, the complex inner product space and the real inner product space. For the complex inner product space, if we start with an operator that's normal, then it can be diagonalized. That's what statement C says. Statement B says we can actually find an orthonormal basis to decompose that vector space, and that orthonormal basis actually is the same as the eigenvectors of that linear map. Those three statements are equivalent. If somebody says, oh, I have a map that's normal and I'm working in a complex inner product space, now you know you can diagonalize that map, or you know that the eigenvectors can be used as an orthonormal basis in that inner product space. That's what we mean by the complex spectral theorem, is what kind of structure do we need? Oh, it needs to be normal, and then we can diagonalize. Those are equivalent. Now, before we jump right into the real spectral theorem, we need to introduce a few more topics or ideas. And one of those is reminding ourselves of the Cauchy-Schwarz inequality, and that was how we bound the magnitude of an inner product by the norms of the two vectors inside that inner product. But we can then look at recalling the property of that absolute value. And that allows us now to have a lower bound and an upper bound, and we are actually going to use the lower bound in our subsequent discussion. Meaning, if we now have the inner product of two vectors, we can find a lower bound on that by negating the norm of the first vector times the norm of the second vector. And that's how we will use Cauchy-Schwarz. What we want to talk about now is completing the square, which is the classic algebra technique that you've maybe seen. If you haven't, it's not that difficult to work through. But here we are actually going to, so keep in mind that this analogy that we've been having with respect to numbers and operators. And when we had real numbers, those were consistent with or analogous to self-adjoint operators. And so keep that in mind when we're talking about real numbers x. Suppose we have the following expression. X squared plus bx plus c, a quadratic. And what I want you to recall is that if we simply look at x plus b over 2 squared, then that will allow us to essentially complete the square relative to the original expression x squared plus bx plus c. Meaning we are trying to, when we square something, we want to end up with the first two terms, x squared plus bx. And we can do that if that second term in the squared expression is half of the second term in x plus whatever. So in this case, we end up with x squared plus 2 times the second term times the first term plus b over 2 squared. Hopefully that doesn't surprise anyone. And what we want to do now is use that structure to try to rewrite our original expression, x squared plus bx plus c. Meaning, if we start with x squared plus bx plus c, we can now rewrite that as x squared plus bx, which is really what we have there. We've now captured bx if we cancel the 2's in the numerator and denominator. And we also have b over 2 squared, but we can't just arbitrarily add in a number, but we can add 0 to any equation, and we can do that by simply subtracting b over 2 squared. And we really want to get the left-hand side, and so right now we still just have the first two terms on the left-hand side, and we can finish up the left-hand side by adding in c. But now we can realize that that piece of that right-hand side can be written as a square. And the square we like because that's always going to be non-negative. That's why we're doing this. Meaning we now have x squared plus bx plus c equaling x plus b over 2 squared. That's what's in blue. And now let's write down the remaining pieces, plus c minus b squared over 4. Question? So we did add that. Right now, what we've added 0. So the question was, what are we doing? I'm trying to make the left-hand side equal the right-hand side. And now what I did is I wrote down the first two terms, and then I added 0, which I'm indicating with the red bracket. And now I know that the left term underneath the red bracket, I can actually collect the 3 terms with the blue bracket and make those a square. Those now become x plus b over 2 quantity squared, as I tried to derive in my note above. But that leaves me then with c with this additional term minus b squared over 4. Is that clear? And really what I'm trying to do is make sure or guarantee that this expression that I started with, x squared plus bx plus c, I'd really like that to be non-negative. And I can make it non-negative or actually positive if I work with that and say if I can keep this term positive, then this whole thing is supposed to be positive as long as that piece is positive, because the first piece is non-negative, isn't it? So now I can say that when c minus b squared over 4 is greater than 0, I can conclude that x squared plus bx plus c is greater than 0. Are we okay with that? Since the first blue bracketed expression is non-negative. But I can rewrite c minus b squared over 4 with some algebra. I can now say, oh, c is greater than b squared over 4, or I could say that 4c is bigger than b squared. And that should look something like what you've seen as a discriminant on a quadratic formula. Now we are suggesting or saying that as long as b squared is less than 4c, then this first expression, x squared plus bx plus c, will be non-negative. And in this case, if 4c is indeed greater than b squared, not greater than or equal to, then we know that that's positive. And if it's positive, then we can invert that number, that expression on the left. Meaning if we now have 4c greater than b squared, we can invert x squared plus bx plus c. Or it remains bigger than 0. Therefore, when b squared is less than 4c, that allows us to say that x squared plus bx plus c is greater than 0. Or x squared plus bx plus c is an invertible real number. That is, that expression, it is not 0 for any value of x. And that simply required a particular structure, x squared plus bx plus c, with the condition that b squared is less than 4c. Then we have a positive number. What happens when we replace the real number x with a self-adjoint operator? Do you see how now we can build things, more general concepts, by just starting with basic scalars? We started with a scalar that was a real number, and remember this analogy. Here, let's go ahead and recall the analogy between real numbers and self-adjoint operators. And with that connection, we can come up with the following limit, which is lemma 726, and that one is entitled invertible quadratic expressions. Which says the following. Suppose that we have a linear operator on a vector space V, and suppose that we put a little bit more structure on that little linear operator, and we require it to be self-adjoint. So now suppose T is a linear operator and is self-adjoint. And suppose that B and C are real numbers such that B squared is less than 4C. Then we can say the following. Then T squared plus BT plus CI, do you see how we've now substituted this self-adjoint operator in the place of a scalar or a real number x? and I is now having to be a placeholder for this identity map, when before in our expression we just had the scalar c. Now this operator, t squared plus bt plus ci, is in fact invertible. Let's see how that comes about. And this is actually kind of fun, because now we have a lot of different properties associated with inner products and Cauchy-Schwarz. If we have an operator and it's invertible, what else do we know? That's kind of a vague, but it's surjective and injective, right? So if we can show that it's injective, wow, we know it's invertible since it's an operator. Or if we can show that it's surjective, oh, we know it's invertible. So with those ideas, let's now assume that B and C are real such that, and this was in the assumption of our lemma, so we're not doing anything other than restating what we assumed in our lemma. So assume B, C are real such that B squared is less than 4C, and we have a vector V that's non-zero. In our vector space V. Now that we have that, let's form the inner product in the with the following expression. Suppose we now take t squared plus bt plus ci and operate on our vector V. And let's now, that's in our first slot. In the second slot, let's just include our vector V again. That's maybe a little ugly, considering how we normally work with inner products, but what do we know about that mess in the first slot? It's simply some sums of different operators, and we know what to do with summations in the first slot. We can apply the property of additivity of our inner product. So let's do that now, or just say linearity, since it's more than just additivity. We're actually scaling by B and C also, so let's call that linearity. Of the first slot allows us to conclude or rewrite this single inner product as a sum of three inner products. We can now say that we have the inner product of t squared V with V plus B, factoring out the scalar from the first slot, which we can do, TV with V, plus C times the inner product of V with itself. We haven't changed anything relative to that first inner product. What we're really trying to show is that that left-hand side, that blue inner product, is positive. So let's see what else we can do. T squared looks a little strange, but how can we maybe break up T squared? So now we can use the property of the adjoint and factor T and say we have TT applied to V. So now we can move that T, the first T, to the second slot using the definition of our adjoint. So the definition of the adjoint allows us to rewrite this as TV T dagger V. And let's now just copy down what we had in the last two terms. But what did we assume as an assumption in our lemma? T was self-adjoint, and that allows us now to get rid of that dagger. in the second slot. So our self-adjoint property of the operator allows us now to say we have TV, inner product with TV, plus B, TV, V, plus C, V, V. Now we can use the definition of our norms, since we have the same thing in our first and second slot, in the first term and the third term. Our definition of norm allows us now to say that that first term becomes the norm of TV squared. Let's leave the middle term alone for now. And we now have C times the norm of V squared. That inner product we want to get rid of. We want to write that in terms of norms of TV and V. And we can do that with Cauchy-Schwarz. Now we need to lower bound that expression that involves the inner product. Meaning we can now say that that's greater than or equal to TV squared minus the norm of B times, since we're bounding things, we need to take the norm of B, but B is real, so that's just taking away the negative sign if it was negative. But we now have B, and now we can say times the norm of the vector in the first slot times the norm of the vector in the second slot plus C times the norm squared of V. And now what we want to do, actually, we have a TV's norm, we have a V's norm. Oh, that's looking like we can complete the square. Let's now complete the square. Meaning, if I now have the norm of TV, think of that as the x. Now I have a minus sign, but that's not really going to matter too much. I can now just say minus something over 2. What do I need to say minus what's the something that's over 2? If I'm completing the square, I want to end up with really this minus B times the norm of TV times the norm of V when I square this piece. And I'm already getting the norm of TV. That's my x, right? So I now need to have the absolute value of B, the norm of V over 2. And I'm going to square that. Is that okay? So that if I square that, I will end up in the second term taking 2 times BV norm of TV. But if I square this, what's the third term that comes out of that square? It's a plus the quantity B norm V over 2 squared. So I need to subtract that, since it will be a plus. So now I have to minus the following. I have the norm of B squared, the norm of V squared over 2 squared, which is 4. And I can't forget what I had up above, which was C times the norm of V squared. Is that completing the square okay, since we've already talked about completing the square with real numbers x? Now I'm substituting this norm of TV, which is just a scalar again. But now I can make that bigger, strictly bigger, by assuming something on the right 2 terms, something about the right 2 terms. Let me first write down the first expression. I have the norm of TV minus the absolute value of b over the norm of v divided by 2 squared. And now I can say, let me say c minus the norm of b squared over 4 times the norm of v squared. And as long as I ensure that this is greater than 0, I'm going to have, because v we said was non-zero. So the norm of v squared is a positive number. And if I ensure that c minus b squared over 4 is positive, then I'm saying that c is greater than the norm of, or I'm sorry, the absolute value of b squared, or I can now say that the absolute value of b squared is less than 4c. But since b is real, if I square b, that's the same as, I can just throw away that absolute value sign. So I can now say I have b squared is less than 4c. Or, what do I now know? I now know that what I started with, this blue expression, is now going to be strictly greater than 0 if I ensure that b squared is strictly less than 4c. Is that clear? So that now I can say, with all of this discussion using all of these properties on the inner products, Cauchy-Schwarz, completing the square, I can now say that this t squared plus bt plus ci operating on v, inner product with v, is greater than 0. Again, assuming that b squared is less than 4c in these real numbers b and c. That's from up here. But now if I have an operator applied to a vector, and that vector is non-zero, inner product with that same vector, and I'm getting something that's positive, what am I saying about that map relative to, and v is any vector. It's for all vectors in the vector space capital V. This is true for all v. What's that tell me about v and where it lives, or what that map has or doesn't have in terms of when would this equal 0? When would this expression equal 0? Well, when v was equal to 0, it would be 0. But let's try a different thing. Let's say that now, let's keep v as non-zero. We'd need the first slot vector to be 0, would we not? So now if the first slot is 0, what's that meaning relative to v? If I have an operator times a vector and that gives me 0, what does that say about the vector? Where does it live? The null space. So now I know that t squared plus bt plus ci doesn't have a null space, does it? If it did, then this expression would be equal to 0 for some choice of v. And this is true for all v, so we know that this map, t squared plus bt plus ci, doesn't have a null space. Or v cannot be in the null space of t squared plus bt plus ci. And v is arbitrary. So if it's not in the null space, then that operator must not have a null space. Therefore, t squared plus bt plus ci, if it has a trivial null space, we also say that map is, it's injected. So now if we've concluded that that map is injective and it's more than a map, it's an operator, now we can go back and say, oh, we have this equivalence between injective, surjective, and invertible. Now we know that that map is invertible. And that's what we were trying to show, setting out to prove. Now we can say that t squared plus bt plus ci is invertible. Given what? Given that b squared is strictly less than 4c. And that was one of the assumptions in our first statement of the lemma. We said given t and its self-adjoint, and we used that self-adjoint property in one of these steps in our proof. We used the property of b squared being less than 4c in the last step, and then we simply had to remember what we're seeing when we have some map operating on a generic vector, inner product with that same vector being positive. That says that that map operator does not have a null space, a non-trivial null space. It has a trivial null space, which is a zero vector, but we assumed v was not the zero vector. We said it was non-zero. That's one of the lemmas that we would need to show the real spectral theorem. Let's look at another lemma. And this one is that a self-adjoint operator has eigenvalues. Or I should say self-adjoint operators have eigenvalues. Which is more than what we could have concluded with just a real operator in the past. If we just had a real operator, we weren't assured that it had an eigenvalue. Now, if we say, oh, we're specializing that operator to be self-adjoint, oh, we then know it has at least one real eigenvalue. Suppose that our vector space is not trivial, meaning suppose it's not the zero vector, and suppose that we also have a linear map T on that non-trivial vector space, and let's assume that that operator is a self-adjoint operator. Then T actually has an eigenvalue. I'll refer you to the text, but it essentially uses that previous lemma. It needs this factored form of a polynomial that we can then show has, in a understanding sense, it has complex roots, which we know then it must be quadratic if it stays real, and we don't have any real roots, but we also have real roots that are guaranteed, and if that's the case, then we have a null space associated with one of those real factors. And if we have a null space of t minus lambda I, if we have a non-trivial null space, then we have lambda is an eigenvalue. That's sort of the thought process behind that proof. Let's now that we have those sort of preliminaries, let's state the real spectral theorem, which when you hear spectral theorem, just think, oh, we're trying to diagonalize something, whether it's a complex inner product space or a real inner product space. And we're now showing what conditions on that operator are needed for that operator to be diagonalizable. And now we can state that for a real inner product space, which is now Theorem 29 in Chapter 7, which is the real spectral theorem. Suppose our field F is real, and we have an operator on that real vector space, real inner product space. Then the following statements, just like in the complex spectral theorem, we're going to show the equivalence or state the equivalence of three statements. Then the following statements are equivalent. A. The linear operator T is self-adjoint. That's more restrictive than when we had the complex inner product space. There we only needed the operator T to be normal in order to conclude the following two statements, or to write down the following two equivalent statements. Here, V has an orthonormal basis consisting of eigenvectors of T, and C, T has a diagonal matrix with respect to some orthonormal basis. So those three statements are now equivalent. If we have a real inner product space and our linear operator is self-adjoint, then we can diagonalize the matrix with the matrix representation of that linear operator. And we're assured that we can find a basis on that vector space consisting of orthonormal eigenvectors. So I'll refer you to the textbook on that, since we've already sort of given you the preliminaries for that. Let's now summarize what we have discussed relative to these spectral theorems. And really what we're saying is, when can these matrix representations of these operators yield diagonal matrices? That's really what these spectral theorems are telling us. The inner product space V, whether that's complex or real, V has orthonormal basis of eigenvectors of the linear operator T, and so here are sort of the combination of the last two equivalent statements in those earlier complex spectral theorem and real spectral theorem, and T can be diagonalized. If and only if A, the vector space, is actually a complex inner product space, and the linear operator T is normal, then it can be diagonalized and we have an orthonormal basis of eigenvectors. Or if our inner product space V is real, don't rest in peace, but RIPS, real inner product space, and T is self-adjoint. Then we can diagonalize these operators, which really is maybe a little bit specific or restrictive. But now if we have a operator that's self-adjoint and we're working on a real inner product space, then we can diagonalize that operator. If we're working on a complex inner product space and that operator is normal, we can also end up with a nice matrix representation, meaning it's diagonalizable. Since our operators aren't normally going to possess normality or being self-adjoint, let's look at more general ways of factoring or representing operators or eventually maps. And the first piece that we will talk about is what we'll refer to as a positive operator. And this is definition 31 in chapter 7. Again, when you hear positive operator, maybe what you should be thinking is this is how we are scaling, expanding or contracting information or vectors. How do we do components? How do we scale components? Either contracting or expanding. Here, an operator, this again is a definition. An operator T, a linear operator on a vector space V, is positive under two conditions. If T is self-adjoint, which really just now says that T is equal to its adjoint, and we need the inner product of T operating on V in the first slot, and in the second slot the vector V itself, we want that to be non-negative for all V an element of V. And really, you might think of this more accurately as saying this operator is a non-negative operator, but the terminology is stuck, or we're fixed with the terminology, and it's just referred to as a positive operator. But really, it's giving us this non-negative behavior. It sometimes can yield a zero inner product in this last condition. remember or note the following. If our vector space is complex, then our linear operator t is actually self-adjoint when tvv is real, which is really implied in that last comment. When we're talking about a scalar being greater than or equal to 0, we're assuming that that's a real number. We can't think of that being a complex value. So when we're saying the inner product of TV with V is greater than or equal to 0, now we're saying that that's a real non-negative value, scalar. But we don't even have to show that if we're dealing with a complex inner product space if we know that T is self-adjoint. Let's try to justify that last comment in the note. One fact that we know is true for an inner product is what happens when we interchange the two vectors in the slots. Then we have to conjugate the scalar, don't we? So the inner product is conjugate symmetric. Is a compact way of stating that. Meaning, if we have the inner product of TV with V, then that's equal to interchanging the vectors in the slot, but then complex conjugating that. I don't know why I'm changing my notation, but now I am. So that overbar means complex conjugate. That's a fact. So now in our note, if this scalar resulting from the inner product is real, then we can make the following statement. We can say that TVV conjugate, if TVV is real, what's the conjugate of TVV? Exactly the same inner product. So the scalar doesn't change when we take the complex conjugate of a real number. Complex conjugate of 4 is 4. So that's a true statement. So if TVV is real, then the complex conjugate of TV is equal to TVV. So we have one result. But if I now look at TVV as far as a complex conjugate, what happens if I conjugate that? Then I can interchange the vectors in the slots, right? So this is now equal to VTV, the complex conjugate of the complex conjugate. Maybe that's why I quit starring. Didn't want to double star. But if I conjugate the conjugate, what do I end up with? This is true because of the conjugate symmetry of the inner product. But if I take the complex conjugate of the complex conjugate, I'm back where I started. Or this is now just equal to V TV. But now what have I said? The left-hand sides are the same, and I end up with this and that. So those two right-hand sides must be equal. Therefore, I can say that TVV, that I've highlighted in yellow, the first one, must equal the inner product of V with TV. And if I'm looking at TVV, I can now move that operator to the second slot by the definition of the adjoint to be V T dagger V. But now what I'm saying is that must equal that. And if the right-hand sides in the last two lines are equal, that's saying then that T dagger equals T, or T is self-adjoint. Meaning, if we know that on a complex inner product space, if we know that the inner product of TV, comma, V is real, we know that T is self-adjoint. That's what we're trying to claim, or that's what we're stating. Let's actually look at, or just state, some examples of positive operators. One, do you remember what we had before at the end of one of those proofs? Look at that inner product. What's that operator in parentheses? Must be positive, right? By the definition of a positive operator. T was self-adjoint, and as long as B squared was less than 4C, this was now going to give us a positive operator. So that expression is a positive operator. The proof of lemma 26 with T self-adjoint and B squared less than 4C produces a positive operator. Where that operator was T squared plus BT plus CI. Another example of a positive operator is every orthogonal projection is positive. If we wanted to cook up some positive operators, then we could just do an orthogonal projection, and that would be a positive operator. And we can do that by construction with these inner products. So now we have this notion of positive operators, and if we have a positive number, if we're now thinking scalars, we can take the square root of that. Now, with these positive operators, we can factor it into two factors, which when multiplied together give us the original operator in terms of matrix representation. Let's now look at a definition of square roots. the operator R, the linear operator R on a vector space V, is the square root of T if R squared is equal to T. And before we look into some examples of that, let me just state a theorem that lists this equivalent relationship dealing with positive operators so that we can start thinking about what we get or what we have when we have a positive operator. Theorem 35 is titled Characterization of positive operators. And this now is just a list of equivalent statements. Given a linear operator T on a vector space V, the following statements are equivalent. The linear operator is positive. Another way of thinking of that is T, and remember how we define positive. It had to be self-adjoint, and this inner product had to be non-negative. Statement B, T is self-adjoint. That's kind of a no-brainer, but from the definition of positive. And all of the eigenvalues, which I'm going to abbreviate as E-values, of the operator T are non-negative. So if you have a positive operator, then if you found the eigenvalues of that operator, all of those eigenvalues will be non-negative. Or vice versa. If your operator is self-adjoint and all the eigenvalues are non-negative, you now know that operator is positive. C, T has a positive square root. In contrast, T could have a negative square root or components that are negative. Just like the square root of 4 is 2 or minus 2. We want the positive one. T, statement D, has a self-adjoint square root. E, there exists an operator R that's linear on the vector space such that the positive operator T can be rewritten as the adjoint of R times R. So all of those 5 statements are equivalent. If you have a positive operator, then you can find a positive square root for that operator. Or you can find a self-adjoint square root. Or you can factor it into an operator that is then made up of its adjoint times itself. Let's look at some examples of these concepts in matrix terms. And here, let's start with square roots. And positive matrices. Suppose the first example is T1 is equal to 1, 0, 0, 0. Can you think of a matrix, let's call it R1, which when multiplied by itself produces T1? Now this one's really hard. Right? So that matrix, its square root is the same thing. You multiply R1 times R1, just put an R1 that looks the same as that R1 on the right of that R1, and what are you doing? You're saying the first column needs to be the first column in R1, and the second column is 0. Well, that's exactly what T1 is. But if that's a square root, you can also say that, oh, if you're just looking for square roots, what's another one? What, when multiplied by R1 hat, what's R1 hat times R1 hat going to give you T1? Just minus 1, 0, 0, 0. So if you just needed a square root, these two are possible for T sub 1. If you wanted the positive square root, then it would be the first one. Let's look at another example. T, or 2. Let's say T sub 2 is equal to 0, 0, 0, 0, 0, 0, 1, 0, 0. We've stepped it up a notch. We've gone one higher in dimension. Yeah, this will be what you have on the final. Yeah, right. You're welcome. It's getting very close to the holiday season. What's one way of creating T sub 2? Is T sub 2 the same thing like T sub 1? If you multiplied T sub 2 times itself, do you get back T sub 2? What do you get if you take T sub 2 times itself? Now I just mentally put T sub 2 to the right of that T sub 2 expression. That's saying the first column's the null column. I'm taking 0 times 0 times 0 of all three columns. Second one's a 0 vector. The third column takes the first column of T1, and that's all 0. I get the null matrix, don't I? So it has to be something a little bit more interesting than just T sub 2 for R sub 2. Is that okay, maybe? Who knows? Depends on what I have next. Will that work? If I now take R2 times itself, meaning over here, I'll do it virtually. What do I get in the first column? That yellow piece says I get 0, right? I'm taking 0 and weighting all three columns. The second column says what? Copy the first column. And what was the first column? All zeros. What's the third column do? Copy the second column. Oh, the second column is 1, 0, 0. Do you see that that R sub 2 now produces T sub 2 if you have R sub 2 squared? So it's maybe a little different than the first example, but it's still a gift if I gave that to you on the final, maybe. If you remembered to show up on, when's the final? Tuesday. It's not a Monday, it's not a Wednesday. We're just trying to test you to see if you're graduate student material to attend the final on a day that you've never attended the entire semester. And what time is it? 6 p.m. They're really stretching us. What about the following? T sub 3. If you want a gift, I'm giving you a gift if I gave you T sub 3, right? I'll say you're welcome again. That's an identity, right? So R sub 3 is giving us, squaring that gives us T sub 3. Let's do a little bit more interesting. Suppose that we have 4, T sub 4, but not to make it too hard yet, let's keep it diagonal. This could be plus or minus the square root of 2 and plus or minus the square root of 3 on the diagonal. True? Let's look at some others. Suppose 5. T sub 5. Let's say that's now 3 minus 4 minus 8, 11. You can verify that tonight. That looks a little different, doesn't it? I don't have any square roots of anything that looks similar on the left. But if you now multiplied R5 times itself, you'll produce T sub 5. How about if I have T sub 6? Already given it away. T sub 6 is now actually the same as T sub 5. But R sub 6 is different. And you can go home and test that out. But one thing that you might note before you go home is what are the eigenvalues of R5 and what are the eigenvalues of R6. R5, if we take its eigenvalues, we'll find that they're at minus 0.2679 and minus 3.732. So they're both negative. And the eigenvalues of R6 are 0.2679 and 3.732. Can we say anything about R5 and R6 relative to our earlier definitions? So now, what would happen on T5? Is it self-adjoint? What would the matrix representation? So now if you went and found the map, the linear map for T5, it would be, let's say, T of xy is going to give you two different coordinates. And the first one would be 3x minus 4y. The other coordinate would be minus 8x plus 11y. That would be the linear map for T sub 5. But here, what I'm trying to show is that, in fact, if we go back to this expression or equivalence, we have to actually have T being self-adjoint and all of its eigenvalues are non-negative, and we can't really say that for T5 or T6, can we? Since T5 and T6 are not self-adjoint, even though one of those sort of factors gives us all positive eigenvalues for the square root. But we can cook up different products to form the same number, and now that we've expanded into higher dimensions than just scalars, it gets a little bit more interesting than just plus or minus 2. Now we have something a little bit similar, but now what's on the right is not that cleanly connected with what's on the left for T5 or T6. So now if you have a diagonal matrix, what do you have? You have a very nice map or linear operator. Now we're trying to go a little bit broader with our brush and extend some of these ideas or talk about other operators that aren't just diagonal. But if we have diagonal operators, those are going to be nice, and we'll be able to more easily determine, oh, they're self-adjoint, and we can look at their eigenvalues very easily because we know they're all on the diagonal. We'll pick up with positive operators and isometries, which are rotations. Positives are giving us scalings, contraction or expansion, and then we'll have to be able to twist, and that will allow us to go anywhere we want in this higher dimensional space. We'll pick up at that point on Monday.